Hi guys, welcome to the video concerning chapter 9.3. This video is part of our chapter on covalent bonding, which is chapter 9. And in this video, I'm going to focus on molecular structure. In the previous two videos, we saw what a covalent bond was, and we saw how to name them, and we learned about how to describe their formulas, and even a little bit about how to draw what their structures might look like. In this video, I'm going to formally go through what a lot of their structures are going to look like and how we can represent that on paper. So the arrangement of atoms in a molecule is very important. This determines not only a lot of the chemical properties of the substance, but also many physical properties such as melting point and boiling point. So it's something that we need to be able to represent clearly on paper in a systematic way so that everybody can understand what we've drawn. Now, chemists have dozens of ways to represent chemicals on paper. I've got 5 very common methods right here. Some of them are new and some of them you've seen. We've seen molecular formulas over and over and over for the last 2 units and even before then, so nothing new here. We've also seen Lewis structures, and these are where we're going to focus. So these are our MVPs right here and right here. Those are the two we're gonna focus on mostly in this class. You can also see several other models. You've got your space-filling molecular model, which shows exactly what the electron clouds would look like. You've got your ball and stick model, which is similar to the space-filling model, but it has these extended covalent bonds so that you can see the separate atoms. Finally, we have our structural formula, which I'll actually define right here. So structural formulas are very similar to Lewis dot structures. You can see they're almost identical. Difference is your structural formula lacks those lone pairs. And since your structural formula lacks those lone pairs, we're actually going to focus on Lewis structures because Lewis structures show everything that a structural formula is going to show, but they have the lone pairs included. And as you guys are going to find out in section 9.4, the increased lone pairs is actually going to have a pretty significant role on how the atoms are going to exist in terms of like space around their central atom, so like their molecular shape. All right, so there's 5 steps for drawing a Lewis dot structure for any molecule. We can read them here. So I would recommend copy these in your notebook and then just take a look at them as we go through this. Just a quick recap. You want to put the least common element in the middle. You're going to put the next least common element in like next to it. For both of those, you're going to put their valence electrons. Then step 3, and this is your most important step. So again, your most important step is going to be step 3, which has you connect the unpaired electrons in each element. That's where you actually form your single bonds. Step 4, if necessary, you want to include multiple bonds, and I'll show you an example of how you'll know when to do that. And then for step 5 is just repeat steps 2 through 4 until you have all of the atoms that you need. A couple of things to note. If your atom does not have 8 pairs of electrons around it, it is not yet done. And hydrogen is only going to have 2 electrons to form that stable octet. Recall that it just has the same number of valence electrons as helium. So I'm going to go through 3 examples here, and I'll follow our process. So let me show you guys what this would look like for something like NF3, nitrogen trifluoride. Hopefully we could name that based on our previous unit. So I'm going to start by drawing my least common element. In this case, that is nitrogen. I'm going to put it right in the middle. So N, check your periodic table. Nitrogen has 5 valence electrons. And then I see that I have 3 fluorines. And based on my scenario here, I'm suspecting that I'm going to have 1 fluorine paired to each one of these unpaired electrons. So I'm going to draw my second fluorine, or my first fluorine here, give it the 7 valence electrons that it needs, and then I will connect my elements. And then we formed our first covalent bond, and then I'll do the same thing for the next fluorine, draw the bond, and then for our last fluorine. So very straightforward with these sigma bonds, these single bonds, right? And of course, after we do that, we need to redraw. So we have our N, F, F, and F, so F3, and then of course we have to put on our all of our lone pairs, right? So each fluorine has 3 sets of lone pairs, and our nitrogen has the 1 set of lone pairs. And things keep deleting, but there we go. I think I got everything. And this would be our actual answer here. So that would be That would be our nitrogen trifluoride. All right, let's do the same thing for a slightly more complicated example with CO2. So I'm going to begin by placing my least common element in the center. So that is carbon, and carbon has 4 valence electrons. I have 2 oxygens, and I'm going to place one on either end of my carbon. So I'm going to put an oxygen here, 3, 4, 5, 6 valence electrons, and I'll draw my other oxygen over here. And this time, give this one 6 valence electrons as well. Very good. So I think with our outline of CO2, you might start to be able to see, like, yes, I'm going to form a bond here and a bond here. Those ones are very nice and straightforward. Those would be my sigma bonds. But I also see that now I've got these remaining unpaired electrons on oxygen and carbon. And so those guys are going to buddy up. I don't know where my carbon's valence electron went. There it is. So those guys are going to buddy up. And then the same thing is actually going to happen to the other oxygen, right? So you can see when you have those unpaired electrons, that's a signal that you're going to have an additional bond there for possibly a double or triple bond. So when I redraw this, I'm going to make sure that I show these shared electrons both being between the atoms. So I'll represent our double bond with the equal sign, almost looks like an equal sign, like that. And then I know that each oxygen has its 2 lone pairs, which I will put on the oxygens. And there we go. That is the Lewis dot structure for carbon dioxide. And you can see automatically from my drawings that these 2 molecules have very different shapes. You can see this one's like almost in a line, and this one makes a little bit of like, we'll see is like a pyramidal structure. But you can see those lone pairs on the central atom have a pretty important role for the molecular shape. All right, last, we're going to talk about actually, I'm going to talk about this one in class. So we'll talk about your perchlorate in class. That one's a little bit more complicated, and I don't want to run out of time here. But I do want to talk about some specific cases. So let's talk about resonance structures. When you have multiple bonds in an atom, it could be the case that there is more than one correct Lewis dot structure possible. So I'm going to highlight this. More than one correct Lewis dot structure could be possible. It's not always the case, but it can be the case. If it is, the molecule would be something like this here. We have a nitrate ion, and if I quickly label my oxygens, just 1 at the top, 2, and then 3, going clockwise, I see that I have a double bond first to my oxygen number 3. Maybe I have a double bond to oxygen number 2, or I could have a double bond to oxygen number 1. And since oxygens are all identical and our nitrogen is just a sphere, they are all 3 of these conditions would be equivalent. So we can write equivalent options. There's no real difference between the double bond going to oxygen 3 versus oxygen 2. And when that is the case, we get what's called resonance, where the electron is actually constantly shifting around in these bonds. And so instead of having 1 double bond and 2 single bonds, instead you have a constantly flowing electron distribution where you have some double bond properties for all of the bonds between nitrogen and oxygen. And experimental evidence for this is actually pretty strong. And that shows that this bond, and this bond all have equal lengths, equal bond lengths. Which, if you recall, the double bonds should be shorter than single bonds. So because all of the bonds are the same length, we know that there is in fact a resonance structure here, and we have the superposition of all 3 states all at once, represented here by option number B. So here we've defined resonance, right? Condition that occurs when more than one valid Lewis structure can be written for a molecular ion. And then I'm going to highlight this part right here. The more resonance that your molecule has, the more stable that ion is. So something like nitrate is a polyatomic ion because it exists in many different forms, and it's very, very stable. So that's partially due to the resonance. Last thing I'll talk about in this video is there are some exceptions to the octet rule when forming covalent bonds. And I just want to talk about one possible condition called a coordinate covalent bond. We will see this sometimes in chemistry. It's pretty common. And so what happens in the event that you have one atom donating a pair of electrons to share with an atom that needs 2 electrons to become stable? In a typical covalent bond, each particle or each atom gives 1 electron. And so they together will have 2. Each one gives 1, they'll have a total of 2. In a coordinate covalent bond, you can actually see for our boron trihydride and our nitrogen trihydride. Well, our nitrogen has these lone pairs right here, and it's actually donating those lone pairs to the covalent bond with boron. So it's different from a normal covalent bond because both electrons actually came from the nitrogen here, but it's similar in the sense that it's still a covalent bond that holds these 2 atoms together. All right, guys, that's all for this video. Thank you guys for listening, and I will see you in the next one.